Hi, my name is Mark Rychnovsky, and I'm going to present a recent work along with Evgeny Dimitrov on a random matrix theory limit for a certain version of the 6-vertex model. The plan of this talk is to first define the boundary-weighted 6-vertex model, then discuss a bit why we choose to study this model, and then prove convergence of a certain observable of this model to a random matrix theory distribution. First, some background. The 6-vertex model is a prototypical model in statistical mechanics. It was introduced by Linus Pauling to approximate the entropy of ice crystals. It's been heavily studied, and it's an exactly solvable model, which ends up being very useful to us because it gives us exact formulas. It's been used to study several physical phenomena. Most notable is phase transitions in magnetism. And relatively recently, it's become one of the standard models used to study KPZ universality. So let's define the stochastic 6-vertex model. This model was introduced by GUE and Spahn in 1992, and it depends on parameters B1 and B2, which are between 0 and 1. It's a probability measure on collections of upright paths in the upper right quadrant of the integer lattice. I've drawn a possible collection of paths in blue here. And I need to tell you what the probability measure is. So first off, there's a rule that no two paths share an edge. And that means that for every vertex in the integer lattice, the paths can do one of 6 things, shown here. And so if we're on a finite square of this integer lattice, the probability of a collection of paths will just be the product of all weights of the vertices, which are noted by 1, B1, B2, etc. here. These are all positive real numbers. So we take the product of all the weights, and that will tell us the probability of getting that path collection. Normally in a statistical mechanics model, we would have to divide by a normalizing constant, but a nice feature of the stochastic 6-vertex model is that that normalizing constant is already 1. We already have a probability measure. If we wanted to find this on the full upper right quadrant of the integer lattice, so not on just a finite rectangle, then we can define it diagonal by diagonal. If we imagine that everything above this diagonal has been erased in the picture, and we want to sample it based on what's drawn below, we can first look at this vertex. No paths enter from below and to the left. So this is the only possibility. No paths enter, no paths leave. Next, we look at this vertex. One path enters from below, so we choose between these two possibilities. We flip a coin with probability B1, and we end up getting this possibility. We continue this process. Here we have a path coming in from the left, so we would choose between these two vertices and choose this one with probability B2. We keep flipping independent coins to fill in this diagonal, and then we fill in the next diagonal exactly the same way, and we can keep going out to infinity. This model has KPZ type fluctuations, and this was proved by Borden, Corwin, and Gorin in 2016. We're going to study a variant of this model. This variant will live on a height n infinite width rectangle instead of on the full upper right quadrant of the integer lattice. We will have paths entering from the left, so n paths will enter, and no paths will enter from below. We will also denote the places at which the paths hit the upper boundary by lambda 1 all the way to lambda n. So we're going to assign weights to all of these collections of paths using the same procedure as before with the same vertex weights. So we take the product over all vertices in this rectangle of the weight of that vertex. But now we also multiply by a boundary term, which is denoted ft of lambda, and is just some positive function that depends on lambda and t. It's an explicit positive function. We're going to think of t as time. It'll be a non-negative integer. Now adding this boundary term destroys the stochasticity, so the weights don't sum to 1. So now to get the probability measure, we divide by the normalizing constant. So first, it's worth noting that when t is equal to 0, our boundary ft of lambda, our boundary weight, is just equal to 1, and we recover the stochastic 6-vertex model. And more generally, our boundary weight ft of lambda is defined in terms of the spin-Hall-Littlewood functions, which were given by Borden and Petrov in a paper in 2018. And this entire measure is an analog of the ascending Schur process for these spin-Hall-Littlewood functions. And it was also introduced by Borden and Petrov in that 2018 paper. This analogy with the Schur process is how Borden and Petrov derive exact formulas for this model that we use to analyze it. So why are we interested in studying this model? The thing that we're going to be especially interested in is some novel limit behavior in the phase diagram. So if we make n very large, so we're looking at a very tall rectangle, and we let t go to infinity, this is an example, a simulation of our path configuration. And this is a picture of the conjectural phase diagram. We can see we have 3 regions, 1, 2, and 3, that are frozen, which simply means that only one type of vertex occurs with very high probability. Here it's crosses in region 1. In region 2, it's empty vertices. In region 3, it's horizontal vertices. And we have 2 other regions. One has GFF type fluctuations, and one has KPZ type fluctuations. And this border between these regions is quite interesting because we're not aware of other exactly solvable models that have a coexistence of GFF and KPZ type fluctuations. And so we have no predictions for what happens at this border. That's something that would be very interesting to analyze. However, at the moment, we don't know the formulas to do this. What we do in this paper is to study the turning point 5. Note that these points 4 and 5 are singled out in the phase diagram. These are called turning points because they separate 2 different frozen regions. And we're going to confirm sort of a natural guess for what happens at this turning point if you believe this phase diagram was correct. It's worth comparing this phase diagram to the simpler phase diagram for the t equals 0 case, which is the stochastic 6-vertex model. And this phase diagram at the bottom has been proved. It is not conjectural. So to understand this turning point, the transition point between the horizontal frozen region and the empty vertices frozen region, we're going to look at the positions at which the lowest few paths take their upward steps. And these are drawn as red dots here. These will be called lambda of pi, where pi is the path configuration. The main theorem is that if we take these lambda of pi's and suitably recenter and rescale them, then in the t goes to infinity limit, we get the GUE Corners process. And the GUE Corners process is the typical limit for turning points in a variety of statistical mechanics models. It's what you would guess should happen if I just told you that the conjectural phase diagram were true. So in some sense, we're confirming the conjectural phase diagram in a neighborhood of this turning point. And just to be explicit, we'll also define the GUE Corners process. So we sample this process by taking an n by n matrix with IID complex Gaussian entries, adding it to its conjugate transpose to get a Hermitian matrix with real eigenvalues, and looking at the upper left justified I by I submatrices. We take the eigenvalues of all of those submatrices, and we list them out as shown here. If this were a 3 by 3 matrix, the top row would be the eigenvalues of the full matrix, the second row would be the eigenvalues of the 2 by 2 submatrix, and the bottom row would be the upper left coordinate of the matrix. So in summary, we have confirmed the conjectural phase diagram in a neighborhood of this point by proving convergence to the GUE Corners process. In a previous work, Evgeny did a similar analysis near this point, starting from different exact formulas. But the rest of the phase diagram remains conjectural. And there's an important work to be done deriving new formulas and analyzing them to confirm this phase diagram. And it would be especially interesting if someone could analyze what happens along this boundary between the KPZ type fluctuations and the GFF type fluctuations, because this is something that people don't have a good understanding of how this boundary should behave. Thank you. Here are some relevant citations, and this is the archive link for the paper.